All right, so today we're going to do more graphs. Graphs are fun insofar as they involve more pictures, and we're doing shortest path today, which I'm sure you've been exposed at least a little bit to before, right? You probably implemented breadth first search or something like this. Okay, so all right, just to warm up, make sure we're on the same page. Here is a directed graph. Your goal is to get from S to T with the fewest number of edges. Yeah, and I'm just going to see what you come up with. I feel like there's always an edge in here where I forgot to draw the arrow. That one. Okay, so I'll let you take a look and we'll see what we come up with, and I'll make sure we all understand the definition. It's the best one so far. 7? Anyone else get 7? I see a few nods. Anyone beat 7? All right, how about this? I'll start here, and then you just tell me like roughly where to go, whether it's the up edge or down edge, something like this. All right, well, you have to say it out loud though. Okay, down. Okay, and then right up or right down? Right up. Right up. Right again. Then what? That. Down. Up. Right. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Anyone beat 7? It was the first time in years we went down to start. I guess it works. There was no 6? I actually don't know. I mean, maybe I once knew. I don't remember. But okay. One sort of funny characteristic, though, it's hard to even tell if you have the right answer. Like if you just stared at it, you're like, I don't know if there's 6 beyond like I stared at it. Okay, so all right, just some preliminary definitions. So that was an unweighted graph with no edge weights, but in general, we're going to have edge weights, and then you're going to sum up these quantities. So, say what's here? Okay, so I guess I'll be using L for edge length. You can use W for weight or something, but today I'll use L. And maybe as a shorthand for summing over a walk, I'll write L with a bar on top or something. So for example, this silly walk here, what would be the sum? Actually, it takes forever. It doesn't matter. It's 11. It took me like 3 minutes to figure that out yesterday. Okay. So with that in mind, we're going to define distance. Does anyone first want to propose a definition for distance? I think we all kind of know what we mean, but to try to give one that's a little more formal. Yeah. Okay, the total sum of the edge lengths to get from S to T. But maybe I should point out, maybe there's many ways to get from S to T. So somehow distance should distinguish between the possible ways. Yeah. Minimal path length. Yeah, minimum. So that's roughly it. So we want to find basically the minimum. One small detail is really going to be the infimum. If the edge lengths are negative or something, you might actually be able to get arbitrarily negative length walks from point A to point B. So usually it'll just be minimum. All infimum allows for is 2 exceptions. One, if there's no way to get from S to T, that'll be positive infinity. Okay, because it's technically the greatest lower bound of this set. And if there's nothing in it, then the greatest lower bound is positive infinity. Or if it can be arbitrarily negative, like pick any negative number, I can find you a walk that's less. That'll be negative infinity. Okay. but minimum is the basic idea. Maybe one simple rule that it's always going to satisfy is the triangle inequality. We discussed this a little. But the word minimum or infimum is kind of giving you this for free. The minimum way to get from S to T is always bounded above by getting from S to U and U to T, insofar as this describes yet another way to get from S to T. Okay, so good. Right. Okay. So you stared at this graph and found some kind of path, and we think it's 7. It's not super clear, but somehow we want to take that exercise and make it more systematic, right? We want to make it automated. So how could I maybe systematically process the graph and walk away convinced that the minimum is really 7? If I have pen and paper, I'm allowed to draw on the graph and things like this. Maybe that's sort of an awkward question. But starting from S, right? I can say, well, these are all the vertices at distance 0 from S. I feel good about this because that's how it works. And once I figured that out, you can figure out, okay, these are all the vertices at distance 1 because that's where I can get to from distance 0. And then everyone I can get from distance 2, see if I do this correctly. Okay, I think these are all the vertices that are 2 hops away. I feel good about that insofar as I feel good about the 1 hop away. Yeah. Once you have 2, I think this one's a little tricky. You have 3, so you can get there and 3, there and 3. I think just everything that's 3 hops away. That weird vertex in the top, actually, you can't get to in 3. 4 is maybe like, okay, I have to actually think. So that's in the 4 category. That one is not in the 4 category. This one is. This one is. Is that everyone that's 4? Is that correct? Okay. So for 5, I can go here. I can go here. I can go here. Which one did I miss? Top right. Top right. Oh, this one. That's everyone that's 6 or 5. 6. Maybe I should just circle them first. Is that everyone that would be 6? Okay, I saw 1 nod, so I'm just going with that. I guess that's 6. And then 7 would presumably be this, our destination that we wanted. And this one, something like this. Okay, so you get some kind of contour layers by distance. Okay, so this is the one prepared ahead of time. But this is like a very natural, systematic way to proceed, right? Okay, you're trying to map out this whole graph. You can start small. You feel very good about 0. Once you've established 0, you can move on to distance 1. And if you really feel like you figured out everyone that's distance 1, 2 is not so hard. Yeah, so you can proceed like this. And if you draw out these contours, this gives us much more confidence that the answer is 7. Right? It's sort of a certificate as well. Okay, so that's, you've of course seen this before. That's the entire breadth first search algorithm. Right? So if you just wanted to do exactly what we did, the most, I think, natural way to go about it, you first establish everything that's distance 0. That's just S. Then for distance 1, I look at everything that's distance 0 and figure out where it can reach but hasn't been otherwise decided yet. That gives me layer 1. Once I have layer 0 and layer 1, I'll build out layer 2 That's everyone that layer 1 can get to, but hasn't already been reached. Okay? So that's all this is doing. It's just looping and increasing this distance counter over time. And here what we're doing is, we're assigning distances as we go along, and those are acting as our marks. So when something has already been assigned a distance, I really don't have to revisit it. I guess if you do it layer by layer, it's sort of clear. And right, so it's not so hard to do this in m plus n time. What's one example? Like, okay, one way to make this run in linear time, right? If I've already built out layer 5, I'll just make an empty list for layer 6. As I find vertices, I just drop it in. Yeah, then I get layer 6, I start a new list, build out layer 7. Okay, so very simple. All right, so that's a linear time algorithm. Now, okay, oh, I didn't erase it correctly. That's okay. All right, so now let's try to prove that the algorithm's actually correct. And I'm gonna kind of take on the following notation. I'll use like just lowercase d for like true distance from S to V. And I'll continue to use this big word distance for whatever the algorithm is setting. Okay, so DSV will refer to the actual distance from distance S to V. And distance is like this table that we're filling out. Okay. And if we actually want to prove it's correct, I really want to, it suffices to show for every one of these values, the set of vertices that get value 10 are the ones with actual distance 10. Ultimately, we want to show that all the distances match the true distances. All the distance labels match the true distances. And what I've done here to get us started is I've just broken it down by that distance level. Okay, so that maybe we can facilitate proof by induction. Okay, so I just want to show that these two sets are equal for every k. The set of vertices I label at distance 10 is equal to the vertices that are actually distance 10. Now I want to do that for every value besides 10. Okay, is this set up? Okay, so I should have erased more, but that's okay. All right, let's start with the base case. Base case k is equal to 0 or something. Seems reasonable. What do we have for the base case? All right, yeah. Exactly. Okay, so let me break it down a little slowly because I think I didn't do a good job setting up. So I want to prove, just for k equals 0, the set of vertices that get assigned distance 0 are exactly the vertices that are really at distance 0. And that's all the mathematical notation is trying to say. And as pointed out, we know that the only vertex that's 0 edges away is S itself. And so we can verify that directly. Okay, so nothing crazy here. I think the mathematical notation makes it look fancier than it really is. Okay. All right, continuing on. Maybe not. Okay. So let's look at the general case. Now I'm looking at, I don't know, distance 10 or something, right? And I can assume by induction that I've correctly labeled everything distance 9 and below. And I just want to take one more step. Okay. So, all right, let's just look. Okay. So ultimately, AK is my set of vertices actually at distance 10. BK is my set of vertices labeled distance 10. And I just want to prove they're the same. I think intuitively we all have the clear idea. The algorithm clearly kind of figures out 9 before it gets to 10. I just want to write that down in some clear fashion. Okay. So I guess there's probably many ways to do it, but the way I set it up is I'm just going to kind of break down what BK is. Okay. So if I look at the algorithm and what the algorithm is doing, right, it's getting all the vertices that haven't already been labeled by one of the previous distances. So it's not in B0, B1, B2. B refers to the things that are already labeled for a particular distance. Okay. And there's some edge from some vertex level 9. Okay, so I'm just kind of expanding out what BK is by reading the algorithm, giving some characterization. And if I look at AK, these are the things that are actually distance 10. Okay, I know that if something has distance 10, it doesn't have distance less than 10. Okay, and I know that to get there in 10 edges, it must come from some vertex that's 9 edges away. Yeah, I feel like I'm not really saying anything deep here. I'm just taking it slow. And at some level, just trying to figure out how to articulate what we all kind of see. Okay, but the point is that BK is sort of defined in terms of what the algorithm does. AK is sort of defined in terms of just distances. And then all I want to point out now is that by induction, I know I get the first 9 levels correct. Right? And if I agree on the first 9 levels, and otherwise the definitions all become the same. Okay, so at some level, all I'm saying is, the set AK is defined as a function of all the smaller AIs. The set BK is defined in the same way, but in terms of the smaller BIs. And by induction, all the AIs and the BIs match. Drop that in, they're the same set. Okay. I feel like this is just making it seem more complicated than it is, but that's just teasing it out slowly. It's really just saying, okay. All right, you all look super excited, so let's just keep going. All right, one thing I want to point out, you've probably seen breadth first search in this form instead, which is something based on a queue instead of a stack. A stack is DFS, a queue is BFS. Okay, so if you wanted to just kind of like make this look slick and you thought about how the vertices are being processed, I could imagine first setting up a queue. That means first comes in is the first one out, just like a line, right? A queue is a fancy word for a line. And I'll first start with S that goes in first. That's the first vertex I figure out. And then I'll pop out a vertex from the queue or dequeue it or whatever. I'll look at all its neighbors and insert it into the queue. Okay, and it'll get processed later. I assume you've all kind of seen this form of the algorithm before. And the way, at least I would prove this is correct, is to just map out slowly that it's processing layer 0 first, then layer 1, then layer 2, then layer 3. They'll kind of be contiguous intervals in that queue. Okay, so same algorithm, it's just some slick description. Okay. All right, that's all I have to say about BFS. Any questions? All right. Let's take the next step. Okay, so now the next step is to deal with positive edge weights. We won't do negative edge weights today. That will be on Thursday. Okay. So now I've labeled all these edges with some integers. I want to get from S to T. Now I'm minimizing the sum of edge weights along the way. All right, so what's the best for this one? As usual, I don't actually know. What's the best you've gotten? Sorry? 15? Anyone else get 15? Anyone beat 15? Okay, maybe that's right. I don't know. But how do I get to 15? I'm here. Up. All right, up or down? And then I guess this last edge to the right, that's 15. Everyone else got this? Anyone beat it? Okay. All right. Okay, so at least we're on the same page. Now, suppose I'm not super worried about running time, just trying to think it through. So this is the graph with integer edge weights in particular. It's not unweighted. But how could I at some level reduce the integer case to the unweighted case. BFS wouldn't be able to take this graph as input, or if it did, it wouldn't do anything correct because it would ignore the edge labels. But if I really wanted to use BFS, how might I go about it? Yeah.
You like split that.
Absolutely. So I can go through and I can start splitting this, right? I split this into 4 pieces. I split this into 3 pieces, 2 pieces, 3 pieces, and so forth. Okay. So you can always discretize the edge weights. Okay. And at least, I'm assuming that you've all seen BFS before and you find it fairly natural to build out layer by layer and things like this. You probably stared at me and wondered why we even had to prove anything. It seems so obvious, right? So the point is BFS is quite intuitive. And I can at least apply that intuition directly here, right? I could imagine first figure out everything, all these intermediate fake vertices, everything that's distance 1, distance 2, distance 3, distance 4. Okay? And at least I'll get the right answer. We're okay about correctness. It's the exact same thing. There's only one issue with that algorithm. It will be a correct algorithm, but it is still wanting in one respect. Yeah. Yeah, so now you start getting running times that depend on the edge lengths, right? Because at edge of length 100, you have to actually do 100 iterations to get there. Okay. And in particular, what's the problem with that? So in particular, of course, that's bad. That's unideal. But it gets really bad if we take into account the fact that 1 million can get represented in log of 1 million bits, right? So you're really looking at an exponential running time, at least if you're encoding the edge weights by standard integers. Okay, so in that regard, it's not really a polynomial running time anymore because you can express exponentially large numbers with a few bits. Okay, so that's the only issue, right? We could do something like this, right? But the issue is the running time. The edge lengths might be very large. We only have an exponential running time. All right, that makes sense, right? Okay, but it's a correct algorithm, so it'd be nice to kind of somehow work with the high-level ideas, so we can at some level almost skip the proof of correctness. Okay, but I just want to now address this running time issue. So in other words, breadth first search is already a pretty good algorithm. It's a logical algorithm, but it's not fast anymore because edge weights can be so big. At least conceptually, how might we try to address this? Yeah. Yeah, we can use a priority queue, but what would that in particular help you do? I'm assuming you've all probably seen Dijkstra's algorithm before, and that's where this terminology comes from. Yeah, I mean, that's what Dijkstra's algorithm does. Okay, at least what I was kind of going for rhetorically at some level, right? Like, if we wanted to sort of simulate what breadth first search does, right? Because we feel good about breadth first search being correct in its logic, right? If you want to simulate what it does, it would be nice to skip all of these kind of fake layers that only have fake vertices in it, right? Like these first 2 layers, it'd be nice if I could anticipate it and kind of go straight to layer 3, right? And then layer 4 has someone, but once I'm at layer 4, layer 5 also has, okay, that's bad. Once I get to layer 6, layer 7 is sort of a phony kind of thing, right? It'd be nice if we can kind of skip ahead, right? Not actually have to process anything because there's nothing really going on. 8 does have somebody, 9 does have, okay, it gets a little complicated. But, from of course you've all seen Dijkstra's algorithm, but imagine trying to do something kind of novel and doing things from scratch. you have this sort of clumsy algorithm that's definitely correct. And now all we're trying to do is basically speed it up. Okay. So that's what we're going to try to do. We're going to try to skip the empty layers. So, right. So you might build out the graph something like this. And now you're only building out a layer every time you find another vertex, a real vertex. Okay. But I think the important point to make is it does guide us in terms of we should figure out the closer ones before the further ones. Okay, so that's what really the BFS logic carries over. It does tell us to find the closest ones before finding the further ones. Okay, so that's the Dijkstra's algorithm. It's not, I haven't implemented it with any data structures yet, so it may not be super fast. We'll discuss this point later. I just want to focus on correctness and things like this. Okay, so what's there to say here? All right, so I start with just distance s is equal to 0. And then I guess each iteration until we've marked all the distant vertices, right? Based on the vertices you've seen so far, right? So I'm going to enumerate all the vertices U that have already been assigned a distance. Okay? And among those, I'm going to look at the edges that leave U, and I'm only going to look at vertices V that I haven't assigned a distance yet. Okay, so these are the unmarked vertices, whatever's the next one, but otherwise kind of minimizing this sum, right? Someplace I've already visited, plus another edge. What's that minimizing sum? I'm not too concerned about the fastest running time in the world. I just want to get the logic down. Okay. And then I'll, whatever vertex that is, the next closest one that's not yet been marked, then I'll write down the distance and I'll repeat. Okay. And I guess the only conceptual point I want to make is you can kind of think of this as breadth first search, but it's just smart enough to skip over, you know, these sort of auxiliary layers that only have auxiliary vertices. But you're processing the vertices in the exact same order breadth first search would. Okay, and then you return all distance labels. So that's the algorithm. Okay. All right. All right, so now I think it's just a point of proving this thing is correct. Okay. And I think maybe some of it is going to be boring. I think the one interesting point is trying to figure out how to structure a proof by correctness. We probably all believe it's going to be correct. It's all kind of doing breadth first search. But I think the interesting thing to point out is, you know, can we identify some kind of inductive or recursive structure? We need something to frame an argument so we can prove it's correct. I'm kind of making a weird point here, but does anyone want to suggest not so much the proof, but sort of how to prove, how to structure the proof? Or more pointedly, if you wanted to do induction, a proof by induction, what can we do induction on? Yeah.
You prove it for everything with lesser distance. With like normal distance.
Okay, so I can maybe try to prove it like on distance. So, okay, so it's something like, okay, suppose the algorithm correctly labels all vertices with distance less than 11. And now I want to prove 11. Yeah, and that's basically what I did for breadth first search. Breadth first search, I was looking for some kind of inductive structure so I can do a proof by induction. And since everything was counting edges, it was very natural to do, okay, let me do 0 edges first, then 1 edges, then 2 edges, then 3 edges. Once I've done 9 edge blocks, I can do 10. Once I've done 10, I can do 11. That's exactly probably how you thought of the algorithm anyway, right? That was very intuitive. That's, I think, very natural. Now, one thing I want to point out is that here things aren't, in my example, things were integer, but if I go to real valued edge weights, okay, now I don't necessarily have like a discrete number of cases before me. Okay, and so in other words, it gets a little awkward to say, okay, I've done distance 11. Now I'm going to do distance 11.00001. And you don't know if you had enough zeros to, you know, skip someone by accident or something, right? So the continuous proofs by induction, so to speak, get a little bit tricky, right? Because you can't really enumerate the real values. Okay, so actually trying to do it by distance value will in any case require significant more care, but maybe I'll discourage us from going down that path in particular. Anything else we can try to do induction on? I'm trying to point out something kind of subtle here, which is, in this continuous space, so to speak, with real edge values and stuff like this, how can I figure out something to do induction on? Induction proof by now we do every single day, so you get more used to it, but it's not clear what to enumerate. Yeah.
Like the order in which this is like added to like the order of vertex like process.
Okay, so there's an idea. So vertices are discrete. Okay, and then one natural order is the order in which the algorithm processes the vertices. Okay, so maybe that makes some sense, and you can that's probably how you understood the algorithm, right? As long as the algorithm gets the first 10 vertices correct, you're thinking it should be able to figure out the 11th vertex. Okay, so okay, good. So that gives us some handle, right? And it's a discrete, unambiguous thing, right? Okay, the algorithm may sort of have its own mysterious things that we're still teasing apart, but there is some order in which it labels things. If I say, oh, let V1, V2, V3 enumerate the vertices in the order they're labeled, I am talking about something concrete that we at least agree on what we're describing. Okay, so that's the first framing. That's maybe the most important part. But now I want to actually prove something. So let's try to fill in, what do I want to claim about these vertices? Yeah, I think just framing and setting up the claim will probably be more interesting than the actual proof in and of itself, because by then you'll probably see the inductive hypothesis. So, anyone want to? Yeah.
But they're sorted in ascending order distance from S.
Yeah, they're sorted in ascending order. So you definitely want to go from smallest to biggest. Okay. What else do we want to prove about them? I think there's actually two things here, and that's one of them. Yeah.
It's the minimum distance from S to that vertex.
And that you're actually getting the right value. So I think, in fact, so usually when I ask this question, that second suggestion comes first, right? Because the thing we ultimately want to prove is that we get the right value. So everyone always says, okay, the 10th vertex gets the right distance and the 11th vertex gets the right distance. But I think it's also going to be very helpful, to know that when I'm doing vertex 10, I've gotten the first 9 vertices by distance from S. That makes sense? So that second point, actually, we would have found to be basically necessary to pull up off a coherent proof. Okay, so we're going to do both of those simultaneously, and it's really doing it simultaneously that will make it a lot easier. If you're trying to just do one, it gets a little more messy. You'll find yourself kind of talking in circles to get around some mysterious block. Okay, so let me clarify. So 1, 2, 3, 4. VI really is the 4th vertex in distance from S, and we'll correctly set the distance for V4. Okay, so I want to do both of those simultaneously, and we'll find that kind of backpacking those two claims together will make it a little bit easy, because then we can, if I wanted to prove claim A and B for vertex 10, I have both A and B for all 9 vertices that came before it. Okay, good. All right, so I think, anything down here? No. Okay, so the usual setup. Maybe this part will actually go more quickly. We've almost done most of the important work. All right, what would be a base case? Not a trick question. If there's only one vertex. So this is on the size of the graph altogether. But I think our claim is actually slightly different. We assume there's some graph, maybe with many vertices, and we're thinking maybe in terms of trying to prove the claim for the first vertex and in the first 2 vertices and in the first 3 vertices. Does that make sense? So we're kind of always staying in the same graph, but maybe I'm going to prove these properties hold for particular vertices at a time. So what would be like the first vertex?
Source.
Okay, the source. So in the base case, thought there was a base case, so maybe there's not. Okay, so in the base case, the closest vertex to the source is the source because everything is a positive or non-negative edge weight. Yeah, and then just checking our claims. Okay, we know the source is the closest vertex to S. Part A is done. We know the distance is 0. That's what the the algorithm does. Okay, so this is also nothing special there. Okay. All right, so base case, I is equal to 1. The first vertex is the source. That's the first vertex the algorithm labels as the source. It has distance 0. It is the closest. Nothing special. All right, in the general case, I is bigger than 1. Yeah, I'm looking at vertex 10. I want to prove that it is, this is the 10th vertex labeled by the vertex, by the algorithm. I just randomly mix up words. This is the 10th vertex labeled by the algorithm. We want to make sure it really is the 10th closest vertex to S. That's what we're imagining. And we want to make sure we give it the right distance. Yeah? Okay, so how can we do this? Yeah. Okay, so if you are the 10th closest vertex, then whatever is the shortest walk to you, the previous vertex must be closer. Yeah, okay, I think that's good. Let's just take that thought and complete it. All right, so that makes if you're, yeah.
Stronger by saying I minus 1. And if you add vertex, then the force be
Okay, so if you are the 10th closest vertex to S and there's some path to you, is the previous vertex automatically vertex 9? The 9th closest? Yeah, not necessarily, right? It could be, I don't know, it could even be S itself is just a long edge to get to me in the extreme case. Yeah. Okay, so yeah, sorry.
the path or the walk that takes S to I must include a subset of the vertices that were all given.
Yeah, so in fact, all the vertices that come before, they're on the path from S to me in that shortest walk, they all must be closer to S. Okay, so that's good. So in particular, like all these vertices are closer to S. At some level, what do we know? Yeah.
We know the distances to all of these vertices, then we could figure out, like, since and we know that the vertex connecting VI to this path has to have been like assigned a proper distance, that we just take the distance from that to the VI, get the distance.
Good. So I think in particular, that wording teases apart something in particular. We want to separate, because we can't take it for granted yet, the true distance from S to each vertex and the distance labels assigned by the algorithm. Okay. So all I know is that I'm the 10th vertex that was assigned by the algorithm. Okay. And the algorithm is labeling me based on some vertex that was already labeled. Vj, where j is less than 9. It can be V5, it can be S, it can be V7. Okay. And I know by induction that all those vertices that came before were labeled correctly. Okay, so all the vertices that come before, I do know that the distance labels match the true distances. Yeah? Let's see what's written down. Hopefully something's written down. Oh no. Okay. So what's going on? Okay, so all right, so if I just go slowly and I just tease apart what the algorithm's doing, right? VI is ahead of some edge. Ahead being like the endpoint, the destination of the edge. Minimizing whatever overall previous distance labels plus the edge, right? This is just stating what the algorithm does. And meanwhile, the ith closest vertex, if we were to define it. So I think the first set of suggestions were all kind of based on this box down here, because everyone was speaking in terms of distances, right? So in terms of true distance, the actual 10th closest vertex, whatever comes before has to be closer to S. So if I had looked at all the vertices that are actually closer, okay, so yeah, it's okay. So if I looked at all the vertices that are actually closer and add an edge to get to me, that'll capture whatever is the walk to the 10th closest vertex. Okay, I feel like these notes aren't great. That's okay. All right, and the only point I want to make here, okay, is that at some level we're looking at the same. If I'm at number 10, I know that for the first nine that were labeled are also the 9 closest. Okay, so everything starts matching by induction. I think I have a new trick here. Okay, they start matching by induction, and they're really the same thing. Okay, I feel like this is all just some like roundabout awkward way to say, if you get the first 9 correct, you can get the 10th one correct. Yeah, so you just look at the definitions. It's all a function of the first 9, whether it's the algorithm, what the algorithm's doing, or in terms of definition of distance. And in this case, they're equal. Okay, I'm way ahead of schedule. Maybe I should slow down. Any questions? Okay, let me just keep going. All right, so let's talk a little bit about running time, first naively, and then going back to the original suggestions in the back. So here's just the pseudocode of the algorithm. If I'm not trying to optimize and use data structures just yet, right? So every time I'm iterating and each time finding the next closest vertex and next edge and all these kinds of things. Okay, so at least naively in this algorithm, again, not trying to optimize anything just yet. How many iterations do I have, of step 2? Number of vertices, right? So each iteration will label one more. Every iteration labels one more vertex. It's big O of n iterations. And now each iteration, you need to find that next vertex, right? We're not using any data structures yet. So if we were to just implement that with loops and stuff directly, how long might that take? Number of edges. Okay, good. You put that together, you have this naive MN running time. And the question, as usual, is can you do better? Of course, it's already been anticipated, but that's the setup. Okay, so we just want to take this out. Yeah. A little louder. All right, so if the ith vertex is already labeled, then what? Sorry?
The different path that already labeled the items. Then if we took a different path, then the minimum distance would be the minimum of that. DAU probably plus the edge. The edge would.
Okay, so so maybe this will enrich the discussion from before. So you're saying suppose I had already found some path to I plus 1, and then I find another path that gets better, and it will go down. It's already better. So are you thinking ahead about trying to improve MN, or are we still talking about this version of the algorithm? Okay, this version. So maybe that's something that's worth thinking through. So maybe that what we sort of took for granted, especially from the BFS, it just doesn't seem to come up, that BFS perspective, right? So our algorithm never relabels a vertex, right? Once it decides it's distance 15, it never revisits this, right? This one we're kind of waiting as late as possible, right? Until I really need to get the 11th vertex and I pull out whatever the 11th is. Now, from a breadth first search point of view, it seems like that doesn't create any confusion if you did layer 1, layer 2, layer 3, right? And then somehow we basically simulated breadth first search by just getting what would be the next vertex that breadth first search would have found. What would have been the next vertex that breadth first search would have found is implicitly what's going on. Okay, so maybe this is, yeah, I'm glad, because I think I was going too fast, so I must have been missing out on stuff. So what we sort of proven, right, is that when we really figured out, we say we labeled the 10th vertex and we have some distance, right? We're also really proving that you'll never find some other shortest path because you missed out on some other vertex, right? Because if we look back at what our proof was doing, it was saying, okay, I want to prove that my 10th vertex is correct. And we're really doing a proof by induction. And that proof by induction is saying, well, the previous 9 vertices, not only do they have all the right distances, but they are all 9 closest vertices. Okay, so once I label me and I turn out to be the 10th, anywhere I'm coming from must have kind of better rank. It must be closer to S. So they must already be resolved. Okay, so it's only by, yeah, so ultimately our this algorithm, the way it's proceeding, it's really just saying, once I figure out the 10 closest vertices, only then do I feel good about figuring out the 11th closest. Once I figure out the 11th closest, only then do I feel good about the 12th closest. I think that's fairly intuitive. And then proof-wise, you want to prove it by induction, and you're saying, well, I want to make sure that I've gotten the 12th one correct. Well, I'm going to assume by induction that I've gotten 11, 10, 9, all of it correct. And once you just kind of set that up, then you say, well, if those are correct, then it's all going to be okay. Yeah, so kind of swept into this proof by induction, but this idea of going vertex by vertex, in distance from S, you are actually making sure that when you make a decision, it's correct, because all the kind of prior information you've actually sorted out. So I think that's we've all seen Dijkstra so many times that maybe we take this for granted, but it's good to tease it out. All right, did that point make sense? Hopefully. Okay. All right, let's get back to this just running time discussion. So naively, this kind of greedy algorithm, it makes sense from sort of a breadth first search or inductive perspective, but it's MN time, right? And our goal is to make this a little bit faster. So I think you already know the answer, so I can solicit from the crowd, how might I try to take this kind of more clearly correct algorithm and try to make it a little bit faster? Or there's some maybe redundancy in this algorithm. What is the redundancy? Yeah.
Looks like we're checking that the same distance is big a lot of times.
Right. So in one iteration, you compute all these distance labels, or tentative distance labels, when you try to find the next closest, next closest, next closest. When you go to the next iteration, most of those values don't change. You discover one more vertex, and that updates some of the values, and the other values don't change. But at least as written as a loop, you just end up reevaluating everything every time, right? So if we just save that information as we go along, right, and we just don't recompute these things, then maybe we could save a lot of time. Okay, so all right, so what we'll do is we'll give it a name. I'll call it tentative distance. Okay, so at some point in the algorithm, you've assigned distance labels to some vertices and the rest are unlabeled. And so for each of those, you can kind of maintain that sort of best value you found so far. Okay, so for an unlabeled vertex V, I'll minimize sort of overall the actual labeled ones, the ones you've decided, the ones you know are correct, the distance plus the length of that edge. Okay, so you're just saving the values so you don't recompute it the next time. Okay, so as you maintain this and you retain this, from one iteration to the next, you're just going to label one more vertex. Okay, so there's only one more candidate. There's only one more candidate for you. And so to update all these values, I can just look at all the edges that leave you, to various vertices V, and just update their tentative distances. Okay? So if you just do this kind of natural thing, saving information, don't reuse things, you should kind of only be updating sort of like along an edge once for every edge, if that makes sense. Okay, so we're just saving our answers. Those values we know don't get updated. Yeah.
So the like 2A and B is like
Yeah, well, so, I mean, I write in a way where the loop isn't quite as explicit, right? But at some level in that sort of pseudocode, I'm trying all V's and all U's where U is labeled and V is not. And now in this second perspective, I'm really focusing on each V, the score, or we call it tentative distance. The best U for every V so far. It could be infinity if we haven't figured out how to get to V at all at any point. Okay. So for every V that I haven't figured out yet, I'll still maintain sort of the best candidate, best way to get there, which again may be positive infinity to indicate we don't even know how to get there yet. Okay, so we're just going to now use a data structure, start saving some information. Okay, and now here's that buzzword that of course came up earlier. All right, so besides maintaining the information, there's maybe one more thing we want to do. We'll want to find the pair UV that minimizes this, but once you have a tentative distance, you're just going to find the value V was the best tentative distance, right? Tentative distance already captures the loop over U for every V. So now all that's left is, after 10th iteration, finding the next best one, next best one, next best one in terms of this, whatever, pre-computed tentative distance. Okay. So now we have something that looks a little bit more like a heap operation. I have all these unlabeled vertices, and I just want to find the next closest, next closest, next closest, updating the closest tentative distance value along the way. Okay. So you can use a heap. Sometimes it's also called a priority queue. All we really need is maybe these three operations. Okay, so it's going to be like key value pairs. Key, I just want the name of the vertex. Value will be the tentative distance so far. So it might originally be positive infinity for everyone because I haven't found anything yet. And as we go along, I label some vertex U, I explore all its edges, I update some tentative distances. And then I might find better paths to yet unlabeled vertices, things that are in my queue. So I want to update that in the queue, and I'll call it decrease, right? Because I found a smaller value. If it didn't get smaller, I don't have to update the heap or priority queue. Okay, and then of course you want to pop out the next best thing, the next best thing, the next best thing. Okay, so you've all taken data structures. If I use the heap, a standard min heap, how long does each operation take? Let's say there's n values and stuff. You remember? Yeah. Well, just a normal heap. Yeah. Log n, right? Something like log n. If I remember, like at least one standard heap is just to maintain like a balanced tree. And things kind of go up based on, so that the smallest value is always up at the top. Yeah, but it gets balanced this way. So you always need log n levels, something like this. Okay, so insertion would take log n. How long would the decrease take? Log n. So, you might find the value in your heap wherever it is. You decrease the value and you just start bumping it up until it can't go up because the parent is smaller. Yeah, so we just kind of keep things in heap order where we make sure the parents are always smaller than the children. And you just go up and down the tree. But the tree only has height log n, so that bounds the amount of time. Okay, and then if I wanted to remove something from the root, yeah. Yeah, do you remember how to do it for a normal heap? Yes, the predecessor. What's the predecessor?
The left side.
Like this one?
So when you
This one. Really? I haven't taken data structures in a while. How do you pop from the top? So at least the version I'm used to is you want to keep like as full a binary heap, from left to right as possible. It might be, at some point more partial like this, but I just want to keep it full, so to speak. And if I just want to keep it full in that picture, not a great picture, right? The candidate would be this one here. This is sort of the last one. And I put this at the top, and now, this is empty. So I still have the fullness. But of course, you have the wrong one on top, right? Because that might be a pretty big value sitting on top. How do I fix it? Send it down. But kind of how do I choose which direction to go? So you do want to go down, but like which child would I pick? Always a smaller one. So whatever is the smaller one, you just keep pushing it back down, and then that'll restore this. There's basically two properties. One, kind of the heap is as full as possible, and the other is making sure that the parents are smaller than the children. And this is almost the only logical way to do that. And everything has height log n, so everything's always log n. Okay, so that's a heap. Everything's log n. So, okay, so we can use vectors like this. So we're going to maintain the tentative values and in a heap this time. That'll help us get the next vertex, next vertex, next vertex. All we're doing is sort of shortcutting and making faster sort of that natural algorithm where you keep looping through. And okay, so I get the next minimum tentative distance. I set the distance label. I look at all the outgoing edges from that vertex I just labeled, and I update their tentative distances. So these will map to kind of also decrease in the key. Okay, you return the distance labels. So if we assume that all the heap operations take log n time, what's the running time of our algorithm and why? Like, for example, how many times do I do these two steps? Or maybe, yeah, how many times do I iterate at least step 3? Yeah, n, right? So each time you remove a vertex that's not labeled yet and you label it, so there's only n. How long does it take to remove the minimum vertex? Just did it. Log n. You set it, that's no big deal. And then here, when I decrease priority key, that will also be log n. So I think the interesting part is how many times do I do step 1? Or step 3.c.1? Sorry? M? Why M?
that's you wouldn't want to what you said like one path. So, and I guess we wouldn't want to take another edge that's like incident.
I agree with the motivation. We definitely want it to be M. But I think what we're saying, okay, the only thing I wanted to point out here. So here we mean M over all vertices N, summing them all up in the sense that each edge is only going to appear there once, right? Only when I look at V will I finally look at this edge VW. It won't appear again. So over the course of the entire algorithm, we'll only do that iteration m times. Some vertices may do it more than others depending on their degree, right? This one has 10 edges, that one has 100, but they'll all add up to looking at each edge once. I think that's the point. Okay, we put everything together. What's our running time of this algorithm? Yeah. M times log n. So that's decreasing the priority every time I look at an edge. Plus what? N? Oh, okay. So m log n times n log n plus n log n. Oh, okay. Never mind. Any others? Yeah. M log n plus n log n. Okay. Yeah, I decrease priority m times. I also remove min n times, m plus n log n. M is probably bigger than n, but anyway. Okay, that much we're okay with? All right, so question is, can you do better? Okay. And so here we have, maybe you've seen it before, and we'll come back to the techniques underlying this much later in the course. But there's a data structure that can actually do a little bit better for you. Okay, it's called a Fibonacci heap. And morally, at some level, it's almost like this was constant time, this was constant time, and this was log n. Okay, so insertion and decrease become constant time, and then removing still takes log n time. But it's not exactly that. Okay, it's using something called amortized time. So let me explain what that is. Well, we can, this is one way to look at it, but it's saying that, look, if I called insertion 100 times, and I called decrease 1,000 times, and then I remove min 25 times, okay? The running time I spend will add up to 100 plus 1,000 plus 25 times log n in hindsight, okay? It doesn't mean that every decrease key operation actually took constant time. Some might have taken longer than others, okay? But after the sequence of operations, when you look back, it's as if each one always took constant time, okay? So at some level, what these amortized data structures are doing under the hood is stuff like rebuilding. Easy, but gradually, like more and more kind of data's getting stale, your structure's getting a little unbalanced, and then you rebuild the whole thing. Every once in a while you rebuild it, but if it takes me 1,000 units of time to rebuild it, but I only do it once every 1,000 steps, that's sort of like one per step. So in hindsight, it'll still always look like constant time per step, but if you actually like traced what the data structure is doing, it might be lumpy. Okay, so amortized running times will always give you something that look good in hindsight, but they have more flexibility. They're actually allowed to have individual operations that are occasionally bigger, as long as it kind of all adds up as if they were all whatever ideal running time. Okay, so we'll kind of exclusively focus on amortized much later in the course. Okay, but if you just thought of those actually being a true operations, you wouldn't be far from the truth. But it's sort of this in hindsight thing. Okay, we're doing okay? All right, so if I use Fibonacci heaps and we revisited our algorithm, okay, we're still doing n iterations. You label each vertex once, and then removing the min, what was the point of this? Okay, removing the min still takes log n time. Okay, but the key point now is that decreasing the priority will take constant amortized time. So it'll be as if it were always constant time, although it may occasionally be longer and occasionally be shorter. Okay, so yeah, okay. So ultimately, you end up spending constant time effectively for every decrease key. Okay, if you put all together, what does your running time become? So before we had m log n plus n log n. Now it's going to be a little bit better, but what is this better running time? M log n. Oh, n log n. Okay, so we'll still pay log n for every vertex, and then we'll still look at each edge once. So you'll get m plus n log n, which probably you've all seen a million times before. Dijkstra's algorithm takes m plus n log n time. Okay. Removing that log n is just some, hardcore data structure problem. Yeah.
Amortized cost that you were saying, where do you see that?
Yeah. So this is still log n amortized. So the algorithm will ultimately do n iterations, each time paying log n. That's n log n. And now here, this used to be log n worst case time. This is now constant amortized time. So if I do it m times, you end up spending big O of m running time total. Some individual operations might actually take longer, and they do. But overall, you'll still spend big O of m total time. Yeah. For the moment, you can just kind of treat this sort of as a black box, and we'll really think about how to analyze amortized things later, because it's a very practical thing, right? It just gives you more flexibility to build your data structure. And you want flexibility. A little bit of the sophistication, moves into the analysis because you need to account for all these things, but it's not so bad when we get there. It's usually one of the more popular parts. But is that okay? This is the famous Dijkstra's algorithm taking m plus n log n time. It's really naturally an m log n time algorithm, and then you can use this very sophisticated data structure. Okay, it itself is only slightly, one step up from breadth first search. It's still the same basic greedy logic. Maybe that's the point I wanted to make. All right, any questions? So I wanted to give one problem that's pretty fun, and then you'll get more practice with this in PSO. So I think last week and this week is particularly fun for PSO, like lots of quick, fun puzzles. Okay, so we did shortest path or distance from S to T, right? Now, suppose I told you that you had to use an even number of edges to get from S to T. You're allowed to repeat vertices. You might find it necessary to repeat or something, okay? But you're trying to get from S to T with the minimum total length. This problem's also interesting if it was unweighted, but the minimum total length, but you're only allowed to use an even number of edges to get there. Does the question make sense? There's only a small bell and whistle on top of the standard shortest walk. Now I'm saying you have to use an even number of edges. So like in this example, if I went 3, 3, 7, 5, I would be using 4 edges, that would be okay. Our original solution, 4, 4, 7, that doesn't count because that's 3 edges. Okay, this is a question. It's sort of, I'm just throwing one small wrench into what we just did. We have some time to think. Any ideas? Maybe I'll give one more minute for everyone. And the answer is not super long once we get there, so we have time. The shortest length of an even number of edges. You solve it? Are you finding it messy, even though it doesn't sound? Anyone want to propose any algorithms? I can write out whatever you have in mind. Yeah. Okay. All right. So can I take like this algorithm here, for instance, and then, so you're going to say, okay, I'm going to store maybe I'll write parity. You'll also maintain like parity or something. A parity of S is equal to 0 because I got the S in 0 steps. So maybe I'm going to do something like Dijkstra's algorithm, but when I get to a vertex, I'll remember if it was odd or even. So that in particular, if I get to T and it was even, then I'm happy. That makes sense. Okay, so the idea is basically you're just keeping track of the parity as you go through Dijkstra's algorithm. Does anyone else have an idea like this? Okay. Now, okay, one issue. Like take our algorithm here, right? So that algorithm will still come up with the same distances, right? It'll just be marking parity as it went along. Our algorithm applied to this graph, the one we just went through, right? It's going to conclude that it's going to get to T in distance 15, right? It's going to mark it, but the parity is going to be odd. So it'll just conclude that you can't get from S to T an even number of edges. Right? That's, of course, not quite the correct answer. So it's more than just keeping track of parity of the shortest paths. Yeah.
Two priority queues, one for odd parity, one for even parity.
Okay. Okay, so I have two priority queues. And I remove something from a priority queue. Well, okay, so what do I do first? Should I put S in both priority queues? Should I only put S in even?
All the edges of S should go to the odd one. So
Okay, I'll put everything in odd. Yeah. Then I'll remove a vertex and I'll label the distance.
Yeah, so whenever you remove a vertex from the odd one, it goes back to the even one. If you remove a vertex from the even one, then that's the final even distance.
Okay, so let's say I'm at S. The first thing I do, right? S is in the even queue. I remove S from the even queue. I take its neighbors. I add it to the odd queue. Step 2 is going to take someone out of the odd queue and look at its neighbors, right? Those neighbors will, I guess, go into the even queue. And what should I do with myself? So I'll just put myself into even, but I haven't even found an even length path. Oh, and I also mark it.
So you don't mark the ones that you take out from odd, but you mark everything that you take out from even.
So I'll only mark things when things come out of even. But is there some risk of like revisiting the same odd?
Yeah, it would be that's like
Okay, so all these solutions, are we mostly imagining opening up Dijkstra as the first step? Let me go to the pseudocode, figure out how to get the words odd and even in there, right? And then it's probably getting messy, right? Yeah.
you just make two copies of every vertex.
Okay, so don't change the algorithm, change the graph. Okay, so I have some vertex set V, right? And what I'm going to do, and it has some edges in it. So what I'm going to do is I'm going to make two copies of the I'm going to make a new graph. Okay, but it's going to have two copies of the vertices. I'll call one V odd and V even. Right, so there's some vertex X, and I'll make an odd copy. Some vertex X, I'll make the even copy. Okay, and for every edge in the original graph, I'll make an edge from the odd copy to the even copy, and an edge from an even copy to the odd copy. Okay, so I've made two copies of the vertices, and I've added the edges in both directions, right? So if an edge went from point A to point B, now it's going from A odd to B even, and from A even to B odd. Okay? Now if I run Dijkstra in this graph, and you carry over the edge lengths, if I run Dijkstra in this graph, and I can get from point A over here to point B over here, I know I'm bouncing back and forth, back and forth, back and forth. And so any walk has to be an even number of edges. Okay, so if I find the shortest path in this graph, that would be some even walk in the original graph. Simultaneously, any even edge walk in the original graph, I can map into here that goes back and forth, back and forth, back and forth. So you need to do an if and only if to prove this thing is correct. That walks in your auxiliary graph map to even edge walks in the input graph, and even edge walks in the input graph map to just walks from even to even, or odd to odd, whichever, same side in the auxiliary graph, so that you know it's kind of sound and complete, right? So make sure you do if and only if. But the real moral is, it took forever to get through the proof of Dijkstra. It took forever to get through the proof of BFS. I saw your faces, it wasn't fun. So don't reprove any of this. Don't open up that box. You know what Dijkstra does. You know how our graphs work, right? So think about how to just change the graph. I'm going to give you all these stories, all these problems, these kind of sophisticated states and things like this, and some will be silly and some will be complicated. But think about how to encode the states in the graph, right? So think about, instead of just edges and vertices, or vertices and edges, think about states and transitions, something that encodes the story. And then you're going to find you can solve a gazillion problems of increasing sophistication. Okay? All right, that's it. Thank you.